Hello, this is the introductory lesson to the Year 12 Kinetics topic. Now, most of what you're going to see in this particular lesson is hopefully going to be background information and will be familiar to you from the work that you did at GCSE. But it's still really important that you take the time to go through this to make sure that you are confident with everything that's come before, because as we continue through this topic and as we go into Year 13, we're going to add quite a lot of additional detail. So, as always with these lessons, what I would like you to do is work through the video alongside the booklet that you're working on. And I would like you to try each of the tasks. Now, you can do that in one of two ways. You can work your way through the booklet until you get to the point where you move on to something new. In this case, you'll see Maxwell-Boltzmann curves, and you can stop there. Or you can go through step by step, try each task, and once you've tried it, review the answer. What I absolutely recommend you do not do is follow the video, pause when you've got the answers and write those in, because you're not going to be able to get that level of understanding and you're not going to be able to check that level of understanding. So you should be making this a challenge. Now, when you've done that and you've paused, you can make your corrections on each task, and you can also send me any questions that you have. So let's get started. We're going to take a look initially at collision theory. And we've got the objectives here. We know what must happen before a reaction will take place. We know that all collisions do not result in a reaction. The examiner's tip here is one that was discussed at GCSE and is important. Later within this lesson, we're going to try to understand why this is the case. Because often in rates of reaction, we consider the idea that doubling concentration or doubling pressure or doubling surface area will double the rate of reaction. We need to know why that's different for temperature. So before we begin, your very first task is just to see what prior knowledge you have. And I really recommend you put down as much as you can. There might be some of you tempted to say, I don't know, I can't remember, and move on. But I want you to really dig in to that knowledge that you have from GCSE, because the more that you can bring back yourself, the more likely it is that you're going to remember it in the future. So when you're ready, move on and we'll take a look at some of the key ideas. Okay, so collision theory. The key parts to this actually are that within collision theory, particles must collide so that they can react. We don't have things done by mediation. We don't have particles drawing up treaties to say that they're going to combine together. They bang into each other, and if they bang into each other with enough energy, they will react. But actually not all collisions will result in a reaction. It's actually fair to say the vast majority will not result in a reaction. They will simply collide and bounce off each other. And the difference between the collisions that lead to a reaction and the ones that don't is that the collisions that are successful, the ones that do lead to reaction, are where the particles have energy equal to or greater than the activation energy. Now, activation energy you will have discussed at GCSE, and we are going to talk about as we begin to understand it more when we move on to the next stage of this topic. Now, you may have written down the impact. I've already talked about doubling concentration, doubling pressure. We've mentioned in our examiner's tip about how increasing temperature increases rate of reaction. But if you've written any of that down here, that's fantastic. But we're going to look at each of those in more detail, carrying on through this lesson. So let's take a look at rates of reaction here. We have a definition for activation energy, the minimum energy required for a collision to result in a reaction. And that feeds into what we've just been talking about. We've got a couple of questions here for you to try, describing and explaining the shape of the graph and telling us whether hydrogen is a reactant or product in this reaction. When you've tried that and when you're ready, move on and review your answers. Okay, so taking a look at it. The first thing is that the graph is steepest at the beginning. That is because there are more particles. We've got 100% reactants. And that means all of those reactants are colliding with each other. Not all of them are successful, but as they get used up, that means that there are less particles left to react, and that means there will be less collisions. And that means there'll be less successful collisions. And for that reason, the rate will begin to slow down. But actually you can see the graph goes flat, and that is when one of the reactants or both of the reactants or all of the reactants have run out. Once we've run out of at least one of the reactants, the reaction can't continue, so there will be no more successful collisions. And at that point the reaction will stop and the volume of hydrogen will stop increasing. In terms of whether it's a reactant or a product, relatively straightforward question, but it's not impossible. It would be asked as an easy mark in the exam. The hydrogen here is a reactant. How do we know that? Well, we started with none of it and we ended up with some of it. The volume has gone up. So if the volume goes up in a reaction, that tells us it's a product. If the graph had been a reverse of this, where we started with a volume of hydrogen and ended with no hydrogen, that would tell us that it was a reactant. Moving on to the next task, have a read of this. Think about what you can deduce from this graph. And there's little bits of information I might be adding that you're not aware of, but I want to see what you can come up with. We have A reacting with 2B to make C. What does it tell us about the amounts of A, B and C? And what information does the graph give us? Okay, now you've tried it, we'll move on. And we can see that B is the limiting reagent. We know it's the limiting reagent because we've ran out of it. The limiting reagent is the one that runs out first, at which point the reaction cannot continue. I've also added on here, this is something that you will need to be very aware of. Square brackets in chemistry now has a very specific meaning. It means concentration in moles per decimeter cubed. So that's what the axis is telling us, that we're dealing with concentrations of A, B and C. In really simple terms, we can see concentration of A has gone down, concentration of B has gone down, they're the reactants. As that happens, the concentration of C has gone up. We can also see though that the concentration of B falls more quickly. Well, that makes sense because 1 mole of A is reacting with 2 moles of B. So we would expect that more dramatic reduction in the concentration of B. And finally, sort of mirroring the idea of B being the limiting reagent, the term we would use for A here is that it is in excess. We have more of it than we need. And we know we have more of it than we need because we still have some of it present when the reaction has stopped. Have another task for you here. We've got diagrams to help you. What do we mean when we talk about things being dilute and concentrated? When you're ready, move on and review your answers. Okay, so I'm going to focus on the idea of concentrated. We can see the one on the right is more concentrated. You might relate this to squash, cordial, whereby you buy orange squash and that's concentrated, but you dilute it with water. So that means you've got less of the orange juice within the given volume. If something is more concentrated, it means we have more particles. Now that is where in exams a lot of people will stop. So we need to add more. It is the fact there are more particles in a given volume. They are more squashed together. This works in terms of concentration of solutions. It also works in terms of pressure of gases. And we're going to talk more about pressure later on. Some questions here for you to try. Have a look at the questions, try and answer them in the space that you've been provided with. And when you're done, go through the answers. Okay, number 1. What happens to the concentration of products over time? We've touched on this already quite a lot. It increases. We know we're making more of our product. But actually, we can go further than that. The rate at which it increases gets slower over time. We can see the gradient getting less steep and eventually going flat. And again, just to reinforce that idea, this is because the reactants are being used up. And that means there are less collisions, which means there are less successful collisions. Moving on to question 2, when and why is the rate in any reaction fastest? And this fits in with the theme of the answer to number 1. It will always be fastest at the very start. That's where the graph will always be steepest. We've got more reacting particles, that means there'll be more collisions, and that means there'll be more successful collisions. And by successful collisions, just to remind you, that means more particles have energy equal to or greater than the activation energy. Moving on to question 3, we've already touched on this many times. Why does the gradient eventually level off? Well, that's because we've used up reactants, and certainly the limiting reagent has been fully used up. So the reaction cannot continue because we don't have the reactants to do it. Question 4, what is the definition of rate of reaction? Now, you might not be so familiar with this, so I'm going to make sure that you have the chance. I want you to note this down, highlight it in your booklet if you didn't get this, if you didn't know it. It's the rate of change in concentration over time, and that's really important. You can actually see that, and we're going to touch on that with question 5, which relates to the boxes that we have, or the bold writing we have just to the right of the questions. But actually, the rate of change in concentration over time, we can also use the units for rate of reaction to help us to remember that, because the units are moles per decimeter cubed, that's concentration, per second, and that's the over time. So rate of change of concentration, mole dm to the minus 3, over time, that's 1 over s, in standard form, s to the minus 1. Let's take a look at number 5, which takes that same idea. And you can see I've highlighted in green so you know precisely where we're looking. Well, one of the bits you need to know from this is that the capital delta, the triangle, means changing. You've seen that with energetics, where we have delta H for energy or enthalpy change. And we can see it here for change in reactants and products, and also change in time. But I'm going to remind you of something that came up earlier in the video as well. And that is that the square brackets tells us we're dealing with concentration in moles per decimeter cubed. So the rate is the change in concentration of products over the time it took, the change in time, for example. Okay, we're going to move on, and we're going to look at how pressure affects rate of reaction. I want you to come up with an answer based on what we've spoken about. When you're ready, unpause and move on. Well, the first thing to consider is that there are more particles in a given volume. And that means there will be more frequent collisions. And if there are more frequent collisions, it means there will be more frequent successful collisions. And if there are more frequent successful collisions, there will be a greater rate of reaction. But I'm actually going to add a level of detail here, something that will be familiar from GCSE, but that I am going to remind and reinforce, because we can actually quantify this. By that, I mean we can start to think about this mathematically, or more mathematically. And I'm going to take the example of what happens if I double the pressure. If I double the pressure, that means I've got double the number of particles in a given volume. So if I double the pressure, that means I'm going to double the number of collisions. And if I double the number of collisions and a proportion of all collisions are successful, it means I'm going to double the number of successful collisions. And if I double the number of successful collisions in a given time, it means I double the rate. Now, we are going to add to this in year 13. It's actually slightly more complicated, but for now, this is a very good start point. I'm now going to ask you to consider how we can model the effect of changing concentration on the rate of a reaction. You don't necessarily need to pause yet. I want to talk through my model and then see if you can adapt it to see how it fits with changing concentration or changing pressure when we look at the impact on rate of reaction. So I want you to consider going to the Trafford Centre on a really quiet evening compared to on a very busy day. And if we do that, we can see that actually the Trafford Centre is still the same size, it's the same volume. So if we go on a busy day, we've got more people, but within the same space. Now, within that, there are going to be lots of different people with lots of different temperaments. And there are a tiny proportion of people who might get inordinately angry if, as you're walking around and maybe looking in a shop window, that you bump into them. Most people will just very apologetically say, "Oh, I'm really sorry," and then you walk on. But a tiny, tiny proportion of people will actually get really angry. Now, if more people are in there, that means that there will be more people who will bump into one another. And that means actually that if there are more people bumping into each other and there are more people, there's going to be more people who are angry when you bump into each other. So how can we adapt that? I want you to try to work out how that model in any way reflects what's happening when we change concentration and pressure on the rate of reaction. When you're ready, unpause and move on. Okay, so I've highlighted here the quiet evening and the busy day relate to the low and high concentration or pressure. On the quiet evening, far less people, lower concentration or lower pressure. And I've also put on here a tiny proportion of people will be angry if we bump into them. That relates to collision theory. Only a small number of collisions are actually successful, do actually result in a reaction. Now, if we take that further forward, what have I got here? In yellow, more people on a busy day in the same space. So again, we're relating that to concentration or pressure. That's a higher concentration or pressure. And more collisions will result in a reaction. If I've doubled the number of people and I double the number of collisions, I'm going to double the number of successful collisions. I'll probably have double the number of people getting angry. Models can be really useful. This is one of many, and it might be something that you can devise your own model to help remember certain scientific principles. But hopefully this is going some way to helping you visualize what's happening in the rather abstract chemistry that we're dealing with. Okay, we're going to move on. We have got here surface area now that we're dealing with. And magnesium ribbon or magnesium powder being reacted above a Bunsen burner. So I would like to know which reaction has the highest rate and have a go at writing a word and balanced symbol equation. Think really carefully about that. You do have the knowledge at your disposal to do it. You just have to think very carefully about what the magnesium is reacting with. Okay, as I said, we're dealing with surface area. We'll explain why in a few moments if you're still unsure, but magnesium powder would react faster because it has a higher surface area. In terms of the reaction, well, magnesium, solid, reacts with oxygen to make magnesium oxide solid. To get the credit for this, you would need to remember that oxygen is diatomic. And once you've got that, you can remember to balance the oxygens and then balance the magnesiums. So we get 2Mg plus O2 goes to 2MgO. What I'm also going to do is show you how we know the formula for magnesium oxide is MgO. And I'm going to go back to my seesaw method. You draw the seesaw out with the positive ion on the left, negative ion on the right, put the charges on the ions on. Magnesium is plus 2 because it's in group 2. Oxygen is minus 2 because it's in group 6. Seesaw is balanced. We need one of each of them, so it's MgO. Now let's go on and take a look at surface area. And you've got one big cube on the left, and we've got that same cube cut up into 4 on the right. How can we use that to explain the impact of changing surface area on the rate of reaction? Have a go, and when you're ready, unpause and move on. So the interesting thing, or the important thing to watch out for here, is that the big cube or square in our diagram on the left has an equal area to the 4 squares on the right. And so it's exactly the same volume of blue reactant. Now, from there, we have got a greater surface area. You can see that as we cut something up into smaller pieces, more of its surface is exposed. And if more of its surface is exposed, that means it can react with the other reactant, in this case, the orange circles. So the greater the surface area, the more surface exposed to react with the other reactant. And again, we can quantify this. If I double the surface area, I'm going to double the number of collisions. I'm going to double the number of successful collisions, which means I'm going to double the rate of reaction. We're going to go on and take a look at a practical that we could use to compare small and large marble chips. I want you to take note that we are using the same mass of calcium carbonate, the same volume and concentration of HCl. And there are different ways you can measure you can measure the mass as it goes down, as gas escapes. We're actually going to deal with the volume of CO2 produced. So the most important thing here is the results actually. I'm going to show you the graph. Remember, we use the same mass of small and large chips, same volume and concentration of acid, and this is the results that we got for experiment 1 and 2, and the small and large chips are highlighted. I want you to have a go at answering these questions. Unpause when you're ready, and we will review the answers. Okay, so why the curve for smaller chips is initially steeper than the curve for large chips? Well, as we've discussed, the smaller chips have a larger surface area. That means that more of the magnesium can react with the acid. It means that we are going to get a faster initial rate of reaction. What do we notice about the mass of carbon dioxide that we've produced in both reactions? Well, we've got the same volume produced. So the same volume of carbon dioxide, even though the small chips reacted so much faster initially. Well, we started with the same mass of magnesium. We started with the same volume and concentration of HCl. So we've got the same limiting reagents. We've got the same amount of product will be made. And that's why we end up at that same volume of CO2. And actually, looking at this, we are dealing with loss of mass. We're seeing that carbon dioxide is being lost. It would still be the same shape of graph if we had volume of CO2. Why does the curve get less steep and eventually reach a gradient of 0? Well, again, we've touched on this earlier within the lesson. As particles are used up, the rate falls because there are less particles to react, so there are less collisions, so there are less successful collisions. And eventually the limiting reagent is used up, so the reaction will stop at that point. We're going to move on and look at temperature. And I've spoken about this already. In all of the others, there is a double relationship. If I double concentration or pressure or surface area, I double the collisions, I double the successful collisions, I double the rate. In temperature, we double the rate every 10 degrees C increase. But it's because there are 2 factors impacting. And we'll talk a lot more about this in the next lesson actually, but we're just getting the idea across. Have a think about what those 2 different ways are, write them down, and then review. The first example is that there are a greater frequency of collisions. Because the particles are moving faster, there are more particles reacting in a given time. But actually also because they're moving faster, there are going to be a greater proportion of them that will have a greater have energy equal to or greater than the activation energy. So a higher proportion of those collisions will also lead to a reaction. As a model, imagine that I got everybody in the classroom, I cleared the classroom out, I gave everybody a blindfold, and I ask you to walk around. And if you did, you would bump into each other, and there's a very tiny chance that that would result in a reaction or an injury, but it's very unlikely. Now, if I then changed the rules and I told you, still blindfolded, to run, you'd bump into each other a lot more, and those collisions would be a lot harder. And you'd fall back on the floor and you would get injuries. It would result in that reaction. Going to finish off with some exam style and actual exam questions that I want you to try and then review the answers for yourselves. At any point you're not sure, send questions through to me and I will get back to you. So let's take a look at these questions, try them, read it really carefully, and then we will have a go. There is a bigger question following on from number 2 that you might want to go ahead and try before you review it. Okay, for question 1, we're told zinc is reacting with hydrochloric acid. We're making zinc chloride. You would be expected to know that zinc is +2, so you would get to ZnCl2, and you need to know that hydrogen is diatomic. In terms of the next question, I'm going to go through step by step to see as fully as possible how we can answer it. I'm going to start by comparing surface areas, and I'm looking at the relative surface areas, whether they're granular or powdery, and I'm giving powder 1 as leading to a higher rate of reaction and granular 2 as a lower rate of reaction. Let's now do the same with the mass of zinc and the concentration of the acid. So the mass of the zinc is either 1 gram, 2 grams or half a gram. Now 2 grams is going to lead to a faster rate of reaction because there is more of it. Half a gram is going to lead to a slower rate of reaction. That's why that's been ranked as 3rd. And the concentration of the acid, a greater concentration means a greater rate of reaction. So depending on whether it's 2 molar, 1 molar or half molar, I've also ranked those, 1 being the highest rate, 3 being the lowest. And finally, I'm going to take a look at the temperature. Now, we weren't told the temperature in the first one, actually. We don't need it to answer this question. But we know a higher temperature. In the case of C, we can see it's 55. In all of the others, 35. We can see that that would lead to a higher rate of reaction. And what I'm then going to do is look through all of these to see if we can determine which consistently is at the lower end of the rate of reactions. And if you do that comparison, it takes you to E. It's granular, so it's a larger surface area, which is slower. It's got the lowest mass of zinc, it's got the lowest concentration of acid, and it's at the lowest temperature. So the correct answer is E. Now let's take this a step further forward, and you might need to look back at the details here as we're going through. This is an 8-mark question. I've actually already put the first one on. I did say it was good to do the whole of this question in one go. 4 different curves, 8 marks. One of them is about the steepness at the start and one is about where it ends. Now if you compare A to B, B has the same volume, same mass of zinc, so it will stop at the same volume. But it will be faster initially because the concentration of the acid is higher. So remember the acid is in excess, so it's the same mass of zinc that means we're getting the same volume produced at the end. If I move on to C, I'm going to make half the volume. I've not done exactly half. You wouldn't need to in an exam unless they actually graphed it, but it is approximately half, and that's because I've got half the mass of zinc. But the zinc here is powdered, which is greater surface area, which means increased initial rate of reaction, so it has to be steeper at the start. And then I've put D and E on here. D, I've got double the mass of zinc, so it will go to double the height, double the volume of hydrogen. And there's more zinc and it's powdered, so it will be faster than A. We're only comparing to A. And you can see that initially it's steeper. And E, well, half the volume, half the mass of zinc, so it will go to half the volume of H2, just as we saw with C, but it will also do it more slowly because of the lower concentration of acid. Couple more exam questions for you to try, and then we'll review. In the first instance, you can see the only difference here is that we're doubling the concentration, so we are going to get to double the amount, and it will be faster. So you're looking for it being steeper, 1 mark, and stopping at double the height. This one is graphed, so it needed to be on the line for the 2nd mark. On B, what we're doing is dropping from 1 molar to 0.4 molar. So we're actually having to go to that bottom line in terms of ratios. Also, because the concentration is lower, we're getting 1 mark for it being less steep at the beginning and 1 mark for stopping at the appropriate height. And then finally, we have got here the difference that we've got here is a higher temperature. So we're not changing the amount of oxygen that we're going to make. So you get 1 mark for it being steeper because of the higher temperature and 1 mark for recognizing that it will stop at the same height as R. In terms of why it decreases over time, we've talked about this multiple times within the lesson. Reactants are used up, so there are less collisions, which means there are less successful collisions over time, which means that the rate of reaction slows down. And that brings us to the end of that reintroduction to rates of reaction. Thank you for listening. Get in touch with any questions and have a great holiday.